Hello everybody. For those of you who've been watching my video channel recently, you will know that I've been working on some power supply projects. I've been repairing some, I've also been working on my own project. One of the things I've found I need consistently is some kind of way of loading a power supply to test its behaviour and to just simply verify that it works. So one of the things I often have lying around is something like this, which is just a simple bulb, 50 watt, 12 volts. Very, very useful. Just connect to the output. You can visually see that it's working. You can get an instant feel for it. Nice and simple. The problem with using something like a lamp is that its resistance changes with temperature. So as you turn it on, as it warms up, it draws a high amount of current. When it's cold, the current starts to drop off rapidly at first, and then gradually for, I don't know, 40 seconds, 50 seconds after. And you can't be very precise about it, but it's, as I say, it's very good, having 2 or 3 of these kicking around when you're working on that sort of stuff. You put them in series, put them in parallel, and do various tests like that. However, what you really want is a programmable DC load. And so during working on these projects, I was thinking about building one, and I'll talk a little bit later about how they work, because they're actually really, really simple, so they're quite easy to build. And in many respects, they're very similar. Electronics is required to make a DC load. The controls and the basic implementation is quite similar. However, for speed and not to have yet another project dependency, I thought I'd just buy one. So I had a look around, and there's lots of them around. They're from very expensive to very cheap, and I wanted something that was reasonable, something I could buy, something I could put straight on the bench and use, and perhaps use as a reference benchmark, as a benchmark if I do build one or design one myself. So I had a scout around, and eventually I decided on buying this one here, which is let me just get the camera on that, sorry. This is a Maynuo M9711. I bought this directly on eBay, direct from the manufacturer. It was shipped from China. Actually, if you compare it to something like a BK Precision or some of the other models that actually look very similar, I don't know if they're the same. I don't know if they're the same internally, but a lot of them look quite similar. And anyway, this one seemed very good value for money. I think it was about $500 or little under $500, including shipping. I had to pay a little bit of import duty on it when it arrived also. So really not that bad. What I thought I'd do today is take it out of the box and just show you what came with it. And then I think I'm going to take it apart and have a look and see what's inside it. We'll tear it down, see what it's made up of, see what's in there, see what makes it tick, and I'll see if I can give you some vague explanation of the internal architecture, how it works, and the pros and cons. We can also look at the build quality, because one of the problems I have seen in buying equipment from China is that the quality is hugely variable. It can be from really poor to really, really great, and you never know, you can't tell. The reason why I've decided to do this video is actually there's really not very much information about these things on the internet. I couldn't find very much. These are a relatively new brand, I believe. So there's very little talked about. There are a few forum posts that talk about these in some detail, and I think I've seen a couple of photographs taken, but I haven't seen a video teardown of it. So I thought I'd give that a go. It's not something I've done before, so forgive me if it's boring. And anyway, we'll give that a go and see how we get on. So first things first, let's have a look and see what comes in the box. And I have actually used this. I put this in the box just for the purpose of this. I have actually used this. I haven't really learned how to use it particularly well yet, so we'll come on to that afterwards. But okay, so the first thing is a manual comes with it. Nothing particularly outstanding. It's a fairly low volume production type manual. You can see it's a classically bound A4 sheets. Laser printed technical manual, technical and user manual. There is a sheet that describes some tests, so I guess they run some tests on it, and it does have the serial number, so I guess they do it per unit when they ship it. That's quite good, so at least they've got some form of quality control there, which is great. So that's the manual. Classic power cord. This is a USB cable. It comes with it. I was a little bit surprised by this, I have to say, because when I opened it and had a look at it, the first thing I noticed is, there we go, M133 isolated. So that's quite interesting that this is isolated, and we'll look at see why that is in a while, to see if that is what I think it is. But definitely an isolated communications cable. It looks like RS232 at one end, although that could just be coincidence. They could just be using that connector, and obviously the other end is a USB 2 connector. So that's the serial connectivity. And the other thing that came with it is software. Again, it's a simple DVR. Is it DVR? CDR, sorry. So they've just blown the software onto a CD. It's not a produced CD. It's actually a burnt CD. So they burn that obviously in the factory. And last but not least is the actual unit itself. Get that out. It's very well packed. I mean, the packaging is really nice. This also came in another box. This box was inside another box, so it was shipped. It was packaged very, very well. It arrived quite quickly as well. I think it took about 10 days from order, so it was pretty fast here to the UK. Also, the unit comes in this large plastic bag, and there we have it. So that's the unit, and as you see, it's M9711. It's the 150 watt variant. There is a 300 watt variant. It was quite a lot more. It was I think about $250 more. So I really didn't need it. In hindsight, maybe I could have done with it. But anyway, this was what I went for in the end. So yeah, it feels quite nice. It's not particularly heavy. It's got this rubber bumper, so it's very Agilent-esque in terms of the physical design. Plastic front. This just fits over. There is no retaining slots on the Agilent. They tend to have retaining slots on here on the Agilent form factor, but on this they don't. As you can see, two very big terminals. I don't like these much. I guess they've done this for a reason. These are not banana connectors. They are, you have to put some specific connectors or wrap wires around the terminals. We've got excuse me. There is a handle that you can either use as a handle or as a stand, so that's nice. There's the rear panel. Power selector, which is great. It's got a sync out. No idea what that does. I'll have to read the manual for that. And it's got the COM port. Now, interestingly, there it says COM, and if you can see there just below, it says TTL. So that's clearly not an RS232 interface. That's some kind of TTL digital interface for the serial. And you can see in here, you can see the heatsink here and no heatsink here. So my guess is that for the 300 watt version, there's another heatsink and so on in there. Anyway, the next thing to do, I think, is to clear the bench and take this apart, and let's have a look and see what's inside. Okay, taking this handle off, you just pull this out and turn it up, and eventually it gets to the point where you can remove the handle just like that. That's nice and easy. Now, this feels really nicely built. It feels quite solid. It's not perhaps not the same build quality as HP kit. We'll have a better look at that when we open it up. It looks like this rear plastic shroud simply removed by removing these two screws. That will come off. It looks like there's four screws here at the bottom, and then the outer sleeve should just slide off. So I'll just go and I'll just do that now, and we can have a look inside. Okay, so we've got it open. So let's have a close look and see what we can see in here. Let me bring the camera in a little bit so we can. Okay, so at first glance, what can I see? Well, the whole thing is built on a single main board, which we can see. It's at the bottom there of the case. The construction is actually all this outer case here is all aluminium, it's folded aluminium, so it has quite a nice quality feel to it. Actually, it's pretty well built. It's not riveted; it's actually screwed together, where the back panel was fitted. On the main board there, I can see looks like what looks like the main power device is. There also seems to be a bridge rectifier on there, quite possibly a regulator. We'll have a look at what those are in a second. There are two other power devices in here, so I'm going to guess that there's 4 power devices on the actual, which make up the active component for the dummy load. Nice mains transformer. Main switch is a real hard switch. It's actually on the board, so the tracks for the mains are actually running along the board, and we can see at this end the mains is directly connected to a connector, which again is right on the board. Quite interesting the way that looks. I wouldn't mind looking at the board, taking it out and having a look at that, so we'll perhaps do that in a moment. These stand out. This is obviously the current shunt used to measure the current being drawn, and you can see that's right up close to these terminals. Those terminals have really substantial straps which are soldered into them. Let me see if I can get a bit of light on that. There you go. They're soldered into the PCB, and then they're bolted over. That's quite nice. That seems to be built really nicely. Obviously, because they're bent in that U shape, that gives some flexibility between the between the case and the plastic flexing. But yeah, that looks good. There's also some fairly high quality capacitors that look like they're strapped across the inputs. That'd be interesting to see what that looks like. I have looked around on the internet for a circuit diagram for this, but there isn't anything that I could come across. The actual electronics on the board, really, there doesn't seem to be that much in there. That looks like a microcontroller of some form. I'll try and work out what those parts are in a second. We'll get the camera closer up. So that looks like the controller. Looks like the rest of the circuitry looks like very classic op amps and various op amps, probably A to Ds, D to As, that sort of things. A couple of regulators, so that looks like local control supplies for running it. You notice in here, unlike a power supply, the transformer here is very small because, of course, you don't need to provide. This is not sourcing current. This is only sinking current. So the only power you need internally is to run the front panel, run the display, and run the electronics inside. The front panel has a fairly substantial. Try and show this on here. It's probably not going to show up so well. A fairly big chip there, U2. Again, I can't quite see the numbers, but we'll have a look at that and work out what they all are. And the front has got a vacuum fluorescent display, so quite a nice display. All right, so I think I'm going to look at this a little bit closer now. See if I can take this apart further and see if I can get the main board out so we can have a closer look. Okay, and I thought I'd point out here, I'm just removing these connectors for the transformer. So this is the transformer primary and the transformer secondary. The build quality of this thing is really quite impressive for what we're paying for. For what I paid for it. There's some kind of silicon sealant which is used to hold these connectors in place. So I had to put a fair bit of pressure on them to work them free. They've obviously paid a little bit of attention to detail there, and that's really good. It's not really what you'd expect in something that is low cost. So yeah, that's really nice. Also, this ribbon cable here, which is a classic IDC ribbon connector, which connects the front panel to the main board. That's also got the same adhesive on it, and it takes quite a lot of effort to get it out. There you can see the silicon sealant that's holding it in place. So I think the way this comes apart now, I'm going to have to remove, undo these bolts here that on the back of the terminals, and there looks like, let's just zoom out here a second. These 4 big screws, which look like they go in through the PCB board and onto the heatsink, so mechanically holding that in. And there's also one small screw here, this one here, which is just a standoff, which is then screwed to the PCB. So I think if I remove the 2 screws here and then remove these 4 screws here and this screw here with these front panels, I think the whole board should just slide out, back panel included. So I'll do that now, and we can have a look. Okay, the last screw there was an earth connector, which is soldered onto the board and ground to the chassis, which is quite interesting. We'll have a look and see why that is in a second. Okay, so there we have the. Let me just. There's a washer just on the floor. Okay, so there we have the board. Sorry about the light reflections. And there's the base of the board. I'll have a closer look at this and see if we can diagnose some of what's going on there. Huge big blobs of solder there. Obviously very, very difficult to get the temperature up on this kind of thing. And given that current shunt is directly soldered, they've obviously gone through a lot of, had to heat that quite a lot and get a lot of solder on there to get a good mechanical connection. Okay, so we'll come back to that in a second. Let's just finish up with this. So the main transformer is bolted in. There's no need to remove that. I'm going to just remove the front panel also, so we can have a look inside. See what that's all about. Okay, there's the front panel. We'll take that apart in a minute and have a look and see what's on the other side of it, see how it's built. And that's it's obviously the construction is they've made a front panel plastic moulding, obviously with a tinted plastic screen for the VFD keypad, which is a rubberized key. So I'm guessing that's straight on the board, and then the board is screwed into the plastic, almost certainly self-tapping screws. I did notice this, that actually when I unscrewed that, this bolt here was loose. In fact, so is that one. So I don't know if that was, I don't think these turned, but they were certainly loose. I guess there's no need to tighten that up too much, but if they were that loose, then there was some possible strain on the connectors. But what's there? Right, so let's have a look at the board in a little more detail. Okay, I've had a look at the circuit and identified most of the major components. So from that, we should be able to build a picture of how this thing works and how it's been implemented. So starting in the main power devices, these are IRFP 250s, and there's 4 of them, two over the rear side of this heatsink and 2 here. They're all wired in parallel. Interestingly enough, they've got source resistors to help ballast the load between those four FETs. Normally with FETs you don't need to do that. You can normally parallel them, and because they have I'll get this right, they have a negative temperature coefficient, which means as they warm up their resistance becomes higher. They're actually normally self-balancing, so you can put as many of them as you like in parallel, and the temperature of each device which will balance the loading. Anyway, they've done that. These are 0.05 ohm, look like 5 watt resistors, so that's how it's wired. So they're the 4 power devices. There was curiously a bridge rectifier here, which I was kind of a bit curious about, but actually having looked at it and metered it out, it looks like it's wired for input protection, polarity reversal. So that's what they're using that rectifier there for, is to help from the best I can tell at least, and someone may correct me if they know this circuit better than I've managed to work out, but that's what it looks like. I wouldn't imagine you could envisage that you could put the dummy load through a rectifier, but that's not the case here, because these input terminals do connect directly to the pins on the power FETs. So the only possible explanation for that is that this, or the only feasible, sensible explanation for that is that this device is actually strapped in parallel and wired out to provide, bidirectional input protection. Don't know, but that's certainly how it's wired. Anyway, that's the power section. It's pretty straightforward. These chips here are TL074s. It's interesting, I thought that almost everything is surface mount here in terms of the chips. That's an LM324 there, except for those TL074s. And I don't know what drove that design decision. The only thing that I could think of was power dissipation, possibly. Although, I don't know, but anyway, there we go. So that's what they've done there. Now the control circuitry. How does all this work? As we know, this connector here goes to the display, so we'll look at that later on. And this connector here is the AC secondaries from the transformer, which runs the control circuitry. So the first thing, the big chip here. This is an 8051 microcontroller. It's actually an 8051F304, sorry, which is a Silicon Labs flash microcontroller, classic 8051 design. It's got an onboard 10-bit analog to digital converter, which it may well be using for various parts of the control, but it's not. That's not the A to D that's being used for the measurement of the current and voltage through this thing. What's being used there is this chip down here, which is a Texas Instruments ADS8327, and that's a 16-bit SAR-DAC, successive approximation register DAC. It runs at 500 kilohertz, so it can do 500,000 samples a second. So I suspect with 16-bit SAR, they're probably doing a lot of oversampling and upping the resolution there, because this thing does seem to measure current down to 4 resolutions, four decimal places, so it's quite high resolution. So at that rate, they can afford to do quite a lot in software in terms of averaging and oversampling. So that's probably what they're doing. The other chip that's worth noting here is this one here, which is a Burr Brown or Texas Instruments DAC 8831, which is a 16-bit voltage out DAC. So that's obviously that forms the key control circuitry for the whole thing. A microcontroller, analog to digital, digital to analog converter. There's a whole bunch of op amps. These are mainly OP07s. There's a whole bunch of those, which are precision op amps. There's some relays here, and there's a couple of IRF 540s here, which I don't really know what they're doing. I haven't tried to reverse engineer the whole thing. I'm just trying to get an overall picture. But there's either those transistors are driving these relays to switch them, and I'm just guessing these relays are switching. Depending on the mode, they're either either switching the sense circuitry to some way to measure the current and or the voltage. But that's essentially the control. Over here we've got the basic DC supply that runs the whole thing. This is a 7812 and 7912 regulators, bridge rectifier, some smoothing caps. That's another regulator there, and obviously there's a fan here. So the fan looks like it's DC controlled. So I imagine that one of these is driving that fan under microprocessor control. I couldn't really see a temperature sensor on here. Now there is a tip 41C here, which is mounted on the heatsink. Now, looking at that circuit, I can't really think of a use for that. What I do know, I could make some assumptions about it. Hopefully it works after that. I can make some assumptions about this transistor and what its purpose is, though. First of all, tip 41 is a very common, either NPN or PNP, I can't remember, silicon transistor. It's very, very cheap, very low cost, TO220 package, so it mounts very easily to a heatsink. And there is an LM324 around here, which is a quad op amp. And if you look at my blog, I've done a written article quite a while ago now, maybe quite a few months ago, when I was first looking at my power supply design, and I've done an article on using a standard transistor or diode, or in fact any silicon junction, to as a temperature measurement device. So, but basically, without going into too much details, because silicon has a negative temperature coefficient, that is, the hotter it gets, the lower the volt drop across the semiconductor junction, the lower the voltage. You can actually sense that, amplify it, and you get quite a linear. It actually works quite well, quite linear, and you'll be able to look back at one of my blog articles and see that work. There's a sample circuit where I was doing almost exactly the same thing. So I'm guessing that's what they've done there. As I say, these devices are cheap, so it's very convenient. You know, in the power supply that I was working on, I'm actually using an MCP9711A, which is a TO92 package like this, and it's just impossible to mount. So I have to look at some alternative, possibly. You know, currently I'm just using thermal glue to glue it to the heatsink. Anyway, so that's what the circuit looks like. Now, one of the things I was really intrigued about was this serial interface for this power supply, and I've had a good look and see how that hangs together. And from what I can tell, well, not from what I can tell absolutely categorically that this D9 connector is a TTL output. It's a logic output, and it's directly connected to the control circuitry over here. In fact, the two tracks run. You can see that these are the two tracks. So I'm guessing transmit, receive. They flip over to the other side of the board, and they make their way right the way round, right the way down here. Come in here and make their way round to here, and I think end up in this microcontroller. Either this microcontroller or they end up in here. I didn't bother tracing it. I don't think they end up in here because of the route they take. I think they come onto this microcontroller. So that cable that we had, that we'd looked at, that come with it, the isolation cable, which I now can't find. They've obviously decided not to build this with an isolated serial interface on it, which is really bizarre, because the amount of electronics required isn't really that great. Now, the only thing I can assume is that one of the problems with providing an isolated serial interface is you actually need an isolated power supply for the isolated side of it. To actually to run the driver. Now, there are ways of doing it on my power supply. For example, I'm using a couple of opto-isolators and driving them at TTL levels, but I'm assuming that the controlling board has a supply on it. So that's possibly the reason why they've done that. And with the USB interface, which is what they've got, if I could find that control cable, it's buried here somewhere. Let's move this out of the way. With the USB interface, you've of course got power from the USB, so that makes it a lot easier to make an isolated interface. So I think that's what they've done. It is the only thing in its, you know, because you could easily go, oh, well, that's really bad design, really poor, and that's, you know, they never should have done that. The only thing I could say in their defence in designing this is not compatible with a normal serial DT interface, which you'd normally see, which would have pins instead of holes. And you know, the problem is, I think, you know, someone that isn't thinking or doesn't know very much could end up trying to make something to make that work, and it is a bit dangerous, because the control circuitry is all directly connected or ground reference to the actual output, and you know, it's it's potentially dangerous. Anyway, it's not fantastic, but it's the only thing I've found really so far that would really concern me. The rest of it is pretty good. A little bit disappointing with the mess that's left on the boards. That could have been cleaned up. This is all sticky. It feels like flux residue that's been left over, and it's all over anywhere where there's this solder at the bottom here. So if you up here, let's see if we can get a close up of that. Yeah, there's an example there, and obviously all these other connectors. This here looks like water damage at first glance. You can see there, but actually that's not. That's just more that flux. It's just sticky and horrible. But other than that. Yeah, not bad. So that's the main board. What I'm going to do now, we'll have a quick look at the front panel controller board, and then I'm going to try and draw a quick block diagram based on what I know about the components that are in use here, and try and present a block diagram of what this DC load looks like. Okay, the mains input is plugged into the board here, and it travels around the PCB basically on these 4 tracks here. So they're reasonably well spaced and reasonably well isolated, mostly from everywhere else. I have to say, I'd much rather have seen that running wires. I have to say, it seems weird, putting the power on board here and then taking it off board here. I can understand the rationale for wanting to mount the switch on the PCB, of course, but yeah, it's okay. There's nothing terribly bad about it. It doesn't run too close to anything. There are tracks on the other side of the board here, which are bridged here, high current tracks, which are bridged to get this mains down here, bridged with a whole bunch of soldered through hole vias. And a couple of vias here, moving the mains around, getting it onto the switch, and the 4-pin connector, which is the primary side of the transformer. So that's how the mains is running on this board. As I say, not brilliant, but they've gone to the trouble of at least putting some warning signs on those tracks. I was curious what this BNC out was, so I've just had a quick scout through the manual, and what this provides you with a 0 to 10 volt linear output, which is directly proportional to the full load of the current, full load current of the DC load. So its full load capacity, depending on its mode, I guess, or its range, you'll get 10 volts out here. At no load, you'll get 0 volts out here. What the manual's suggesting is you use that to connect to the scope. To monitor the output, so you can see the output waveforms on the DC load. On the output, we've also got these this terminal block connector. There's 5 terminals. We've got 5 terminals. You've got ground, trigger in, trigger out, and plus or minus sense. So it's quite nice because these terminals, obviously, and the cables that you would use to connect them if you're doing really high current work, the cables themselves would have power losses in them from the resistance of the cable. So this remote sense allows you to connect some sense wires up to the actual source of the load itself. Of the power itself, and then the DC load this load will compensate for the losses in the cables, which is quite nice. Trigger in, trigger out. This has as well as the normal constant current, constant voltage, constant resistance type modes. It's got a pulse mode, so it's got a mode where you can set it up to pulse on and off, or from say 5 amps to 10 amps on a regular basis. You can set the frequency, set the mark space ratio, from what I can tell, which allows you to test the dynamic response of a power supply. So that's where this this BNC out comes, because if you pulse load a power supply and look at its behaviour by looking at the output terminal on the load, it allows you to look at the dynamic behaviour, the behaviour of the regulator in the power source. So that's what that does, and that's what those terminals. Okay, quick 5-minute chat about the basic principles of a DC electronic load. There's nothing complicated at all. Any load requires a power source in order for it to be a load, so that's obvious. So the input terminals to a DC load marked positive and negative. This is obviously a DC load, so positive and negative. The input terminals are what you connect to the power source. And then inside the DC load, we've got a power device, a FET or a bipolar transistor, or a whole bunch of FETs paralleled or whatever it may be, essentially strapped across the load. So as you put more drive in, this FET will conduct and it will place a load. All of the power that the load consumes from the power source will be dissipated effectively in the power FET. So it's important that these FETs are able to withstand that, and obviously heat sinks and cooling is very, very important. But that's the basic principle. Now, a typical, very rudimentary or basic constant current, a very basic rudimentary DC load is effectively a constant current source. And so if we have a look at this in constant current mode, the way it works is very simple. You've got the FET, as I've described, across the load. We sense the current in the circuit, and we feed that current. Current sense back into the error op amp, which drives the FET. So whatever voltage we set on here will set a proportional amount of current to be dissipated through this circuit, and it effectively a simple DC servo will hold that all in check. So that's a typical constant current source with a voltage driven a voltage reference to drive or set the current that's driven through the circuit. In constant voltage mode, it's very similar, except for now we're not interested in current anymore. What we're interested in is how much output, how much voltage is across the output terminal. So we sense the voltage using an amp, and we feed that back into the error amp. And so whatever voltage we set here on the positive input of the error amp is will control how much voltage is allowed to be across these terminals, regardless of the current flowing through the circuit. And that's, as long as that's within the overall dynamic range of the circuit, that's exactly what it will do. So in that mode, it's a constant voltage mode. If it needs to provide constant power, then a different circuit would use, and in order for this to be fast and responsive, there's a whole bunch of op amps inside the actual power supply, but you would have a different kind of configuration. You would sense power by summing the output of your current sense with the output of your voltage sense. You would sum those two together, and that's what would drive the input, the negative input of the error amp, and you'd set the voltage to set the power. And in the case of constant resistance, again, you'd need another circuit, another op amp, or another configuration. Let me think. I'm not sure I'm thinking clear enough now to. So to get constant resistance, you would probably subtract current from voltage. Was that right? Well, I'm not sure. Anyway, whatever you would do. So another analog circuit to, and effectively you'll drive the error amp with those particular circuits. So that's a very, very rudimentary DC electronic load. The basic principles of how it works. These are really easy to build. You can lash one up in a few minutes with bits of junk that you've got laying around if you don't want real precision or anything. It can be done really, really quickly and really easily. Okay, so on to the Maynuo M9711 block diagram. There's 4 power devices. This is the 150 watt version. So there's four power devices in there. They're FETs, they're IRFP 250s. What's slightly curious about this is that as well as having 4 power FETs, those in parallel, they've used ballast resistors, I suppose, that are there to balance the load in these 4 FETs. Now, that's actually very, very typical when you're using bipolar transistors as the power devices, but it's quite unusual when you're using FETs, as far as I'm aware, or certainly what I've seen. So why is that? Well, in a bipolar transistor, you've got a negative temperature coefficient. So what that means is, as the bipolar transistor gets warmer, the voltage drop across it becomes less. and as the voltage becomes, as the transistor warms up, because the voltage drop across it becomes less, its effective resistance is lowered, and so it takes more of the power from the load, and effectively the other transistors stop working until it self-destructs, because it will keep on getting hotter, taking more power, getting hotter. So you have these ballast resistors, or emitter resistors, as they're often configured, or to balance that, to help balance that load. FETs, on the other hand, though, have a positive temperature coefficient, which means as they get warmer, the resistance across them becomes higher, and therefore they will share less of the load, placing more load on the other devices which are running cooler. So even if they're unmatched, they will still balance each other out, and they really don't need these resistors. So I don't know why they've done that. Maybe someone can enlighten me, but as far as I'm concerned, that's really not needed. Anyway, they're there. They're 5-watt resistors, and they're 0.05 ohms. Then, as described in the previous block diagram, an amplifier measuring current, an amplifier measuring the voltage across the terminals, an op-amp, an error op-amp, and some kind of way of selecting either constant current or constant voltage mode. And as I said before, there's quite a lot more complexity than I'm showing here in the actual DC electronic load. So I imagine that there's specific amps for dealing with constant resistance and constant power. That, just bear in mind that that's more complex than what's in there, but it's a reasonable guide, so at least you know what's going on. Then we've got the DAC, the DAC 8831, which is used to derive the reference to drive the error amp. And we've got the ADS 8327 analog to digital converter, which is taking the measurements from the constant current, and from the current measurement and from the voltage measurement. The heart of the whole thing is an AT51 F304, and then the front panel display is a VFD display being driven by a PT6314 driver, VFD driver chip. The interface to that can be parallel or serial. I'm not sure what it's using. I suspect it's probably serial because of the number of connections. You've also got the front panel keypad and the front panel rotary encoder also being controlled by the 8051. And there's a separate small power supply just to power all this circuitry, which is it's very, very simple, winding on the mains transformer, plus or minus 12. I think it probably derives other voltages as well, which drives the rest of the circuitry. So it's really that simple. There's nothing complicated in there. It's quite straightforward and easy to understand. I imagine it would be relatively simple to fix if anything went wrong with it, and that's what it looks like. Okay, something else I wanted to cover, just talking about the mains earth and the isolation of the output terminals, the positive and negative output terminals. So having checked internally and metered it out, the positive and negative terminals are definitely floating in relation to mains earth. So all of this circuitry, everything you can see in here is all tied to the negative terminal of the load on the front panel over here, but it's not tied directly to mains earth. It is isolated. And the one thing to be careful of is this serial output, because obviously these TTL level signals are referenced relative to 0 volts, which of course is tied directly to your load. So if you're in a situation where you've got, if you didn't use the manufacturer provided cable, which is an opto-isolated serial interface, and you tried to knock something up or tried to connect this without being aware, you could find that you could do the equipment or yourself some damage. Okay, so it's all back together now. I've just put the mains on. Let's make sure it's still working. I'm pretty confident that it'll be fine. There we go. It's powered up and it's working fine now. You remember I said there was relays inside, and I was keen to know which ones of these modes changed the relays. So when I set it to current, it's already on current. So when I set it to voltage and press enter, the relay clicks, so I can hear something clicking in there. When I set it to current, I hear it click the other way. So definitely switching between voltage and current. However, once you're in voltage mode, which is there, setting it to power or setting it to resistance, so resistance like that or power, changes the relay. The relays don't click if you're already on voltage. So if you hear me, I'm on power at the moment. If I set the voltage mode, if I set the voltage mode, it clicks. So in voltage mode, but once it's in current mode, like that, setting it to resistance or setting it to power, there's no relay clicks. So power, resistance or current are all the same mode. So obviously in that block diagram that I showed you, only in voltage does it switch to constant voltage mode. In these other three modes it seems to operate in constant current mode. I haven't really thought about whether that's good, bad, right or wrong. It just is what it is. So there it is working. What I'm going to do now, I'm going to go and read the manual, and I'm going to test out one of the pulse modes because I'm interested to see that work. Then I'll set this up with a scope and with a power supply, and we'll put one of the Agilent power supplies into with a pulse load on it, and we'll have a look at the output and see what it looks like. Okay, I'll see you in a minute. Okay, so I just set this up, connected the scope. I've got channel 1 on the voltage output, channel 2 on the current output. I read the manual, figured out how to program this, and what I've done is I programmed it to, this is a 0 to 25 volts 7 amp power supply. It's one that I'd done a teardown and repair on. I programmed this to basically pulse the output 200 milliseconds off, 100 milliseconds on, drawing 100 milliamps in the off state, drawing 3 amps in the on state. Got it running. Was looking at the waveform scope, and suddenly massive explosion right out of this power supply. So I haven't opened this up or had a look. I can smell a little bit of burning. No idea what's going on. It definitely something bad broke in there. So I'm not quite sure. I'll have to take it apart and have a look. So this one that I repaired is now once again bust and broken. Not really good, you know, from the power supply's point of view. It's really poor that would happen. But maybe there's something I don't understand. But to have a pulsed output there at that sort of speed, which is, you know, a 10 hertz square wave, really shouldn't have blown it up. But there we go. That's exactly what's happened. On to the next test then. Okay, simple test. I want to basically put a load on the power supply. Basically a square wave. I want to turn it on from a you know, drawing in constant current mode, a limited amount of current to you know, maybe half its capability, say 3 or 4 amps, and I want to turn that on and off you know, at a fairly reasonable rate, so we can look at the dynamic response of the output on the scope. So the way you set that up on this load is pretty easy. You press Shift 6, which is set tran, and what that means transition from A to B. So level A current is going to be 200 milliamps. I'm just going to enter 100 milliamps in there. Oh, sorry. Let me just do that again. Shift 6. So let's have 100. Sorry. Getting this wrong here. Shift 6, 0.1. So 100 milliamps for 50 milliseconds. Rising time will be instant. We want a square wave. Level B, we want to go up to 4 amps. Hold that for 25 milliseconds. No full time. And the transition mode is continuous, which means it will run continuously. So on the power supply, I've set it to 8 volts output. Set a current limit of 1.5 amps. I'm not sure if I should open that up a bit. Let's open that up to 4 amps. Okay, so turn the supply on. Now I've got the scope connected here, so this channel 2 is connected to the trigger output on the DC load, and if you remember, that's meant to give us 0 to 10 volts for the current output, for the current that's being dumped into the load. So that's monitoring that, and I've got the channel 1 here on the straps across the output of the power supply, so we can monitor the voltage there. So turn the power supply on, we can see the voltage go up. We're at 8 volts dead. This is seeing 8.1 volts, and then run it, and there we go. We're getting the square wave. So here, this is the square wave we're generating, because this is the current that it's drawing current, then it's not drawing current, it's drawing current, then it's not drawing current. So at that peak, it's drawing 4 amps, no current. 4 amps, 100 milliamps, 4 amps, 100 milliamps. You can see the output waveform there is it looks pretty good, really. What I'm going to do is just let me just AC couple the output there, so we can actually wind up the gain there and have a look at what that looks like. So the dynamic response of this power supply is actually really fast. I mean, you know, if that's anything to go by, you know, that's as good a square wave on the output. You can see the power supply responding, very subtle slope, and a very subtle slope coming up here, and that is, where are we? We're at 100 millivolts of division. So load regulation, you're seeing about, I don't know what the correct terminology for this, but you're seeing about 50 millivolts of deviation there, going from 100 milliamps to 4 amps. Now when I've done this same test with these same settings broadly on that other power supply that I repaired earlier, as I said, it exploded. So clearly, you know, I'll have to look at that and find out why that is. But this is behaving as I would expect, and you can see that the output voltage is rock solid. The current is jumping up and down as I would expect given the setup. So there we go. So that's the basic DC load up and running. This is a really great way of testing the dynamic response, and this is what I need to be doing to the power supply that I've been working on myself, building myself. Is you know, one of the reasons why I've sort of taken some time to look at this is to learn how to use it, so I can do some similar tests on my power supply, and hopefully that doesn't explode like that 3634A did earlier on. It's a real shame I didn't catch it on camera, because it was quite spectacular. It made a really loud noise, then it exploded with a big flash, and then I heard a loud hum coming out of the mains transformer before I managed to hit the power switch. So. Okay, in summary then, the Maynew M9711 DC electronic load. I paid £330 for it, which I think is pretty good value for money. The build quality is really good. You know, for what it is, it's made by a company that's certainly I've never heard of. Relatively, they do have a broad range of power management products. So they've obviously got some substance to them, but a Chinese manufacturer, as I said before, stuff that's manufactured in China can be anything from really great to really poor, and I'd certainly put this more towards the great side. It's pretty good device for the money that I paid for it. Pretty good value for money. It's probably about right, really. I mean, I would say some of the other DC electronic loads that I was looking at, which were maybe twice the price of this, are probably overpriced, or maybe we're paying for the brand, or you know, that extra little bit of quality. But you know, overall, really built really well. As I say, the overall circuit and the concept is simple, so it's quite easy to implement well, and they've done a really good job at doing that. Constant current, constant voltage, constant resistance, constant power, pulse mode, so you can test the dynamic behaviour of a power source. So really, it's got external reference output, so you can see the power being dissipated in device in real time, which is fantastic for measurements. Remote sense capability, which it's got, which is really good. External trigger input and output, so you can trigger the pulse mode from an external signal. You can also trigger your scope or your measuring equipment from, or other measuring equipment from, the trigger out when it's pulsing continuously. So yeah, it's got a lot of functions and features, works really well, and you know, I'd say for the money, you know, I'm pretty pleased. So the big question, you know, having bought one of these myself, would I recommend one of these DC electronic loads to a friend or colleague that needed to buy and use a DC electronic load? And I think that the answer there is a resounding yes, I would. So there we go. All right, so I'm done now. I hope you enjoyed the video. I hope you enjoyed the teardown. And obviously, if you're looking to buy one of these yourself and you've come across this video because you're searching for it, hopefully my efforts here will save you from buying one and then tearing your own one apart and perhaps possibly invalidating your warranty if you're curious to know what's inside. Hopefully the videos are detailed enough to give you a good sense of what you'd find in there if you opened your own one. That's it. If you enjoyed the video, please give it a thumbs up, and I'll see you next time. Thanks very much for watching.